In this video, we are going to talk about resistors in series, resistors in parallel, voltage division rule, current division, and current division rule. So after watching this video, you should be able to recognize resistors connected in series and parallel. You should be able to use the rule to combine connected resistances to find an equivalent resistance, and then be able to use voltage division, current division to solve circuit. Now, so let's talk about when we said the component are in series. So we said that the element, right? So element are in series. Okay, that's a series connection. Okay, so we said that elements are in series okay, so series element, okay, carry the same current. So particularly we are going to talk about resistances. So when we have this power supply, okay, and let's say we have R1, and then we have R2, have R3, have R4, have R6, and R5. So the current I here is the same current here, is the same current there, and that's the same current supplied by the voltage source Vs. So the current is the same through R1 to R5. So we say that R1 to R1, R2, R1, R2, R5 are connected in series. Okay, so let me level the voltage across this element. So we have V1, okay, VR1, VR2, VR3, VR4, VR5, VR6. So what do we have? We know that VR1, when we apply Ohm's law, is R1I. VR2 will be R2I. Using the passing sign convention, they can different from plus to minus. VR3 is R3I. And so let me enumerate all of them. So V R4 will be R4 I V R5 equal to R5I, and VR6 equal to R6I. So we learn KVL from our previous video. So when I write KVL, I'll have negative Vs plus VR1, right? So let us write KVL. So let us write KVL. So that gives me negative Vs starting from here, right, moving clockwise, plus VR1 plus VR2 plus VR3 plus VR4 VR5 VR6 equal to 0. Now, so that means Vs equal to R1I plus R2I plus R3I. Substitute V1 and V2 and V3 and all the through V6 by their Ohm's law. So R5, R4I plus R5I plus R6I. So because the current is common, that gives me R1 plus R2 plus R3 plus R4 plus R5 plus R6 times I. So I'm gonna call, so R1 plus R2, right, plus R6, right, so R3 plus R4 plus R5 plus R6 is an equivalent resistance. So we call it R equivalent. So that means Vs equal to R equivalent times I, where R equivalent is the sum I from 1 to 7 to 6 of Ri. Okay, so there's this network that we have in here. Okay, when I paste it down here, so let me copy this again. And let me paste it here. So this is equivalent to this voltage source Vs, right, in series with this resistor that we call R equivalent, which is the sum of the resistances, and the current is the same. The current I is the same. So the resistances in series will be combined into one resistor, so we just add them up. So in general, okay, so when we have n resistances in series, So we have R1, R2, okay, R3, R4, and then let's say we have Rn. Okay, so the equivalent resistance R equivalent will be R1 plus R2 plus R3 plus Rn, which is the sum in compact form I equal to 1 to the n of Ri. Okay, so when you have resistances in series, you can just combine them into one by adding them up together. Okay, so that's the for series resistance. Now let's talk about parallel. Let's talk about parallel connection. Okay, so yeah, parallel resistances. Okay, so resistances are connected in parallel. We defined this in our previous video when they share the same common node, two common nodes, when they share two nodes. So let me explain. So let's say that I have this voltage source Vs, and let's say that I have R1 and have R2 and have R3. Let's say that I have, this is R4. Okay, so we have, this is a node and this is a node, right? It's a node, this is a node. So this R1, R2, R3, R4 share the same common node. So if I call this A and I call B, right? So R1, R2, R3, and R4 share the nodes A and B. Okay, so they are connected in parallel. Okay, so as you can see, the voltage here is also Vs. The voltage here is also Vs. The voltage here is also Vs. Also, the voltage here is Vs. So let's call this current I1. Let's call this current I2. Call this current I3. Let's call this current I4. So, and then let's call this current the total current. Okay, so when we write KCL, Kirchhoff current law at node A. So we have the total current is the current that's flowing to the node, right? This is I total. So I total equal to I1 plus I2 plus I3 plus I4. Okay, so by Ohm's law, tells us that Vs, which is the voltage across R1, right? So if I write VR1, right, which is equal to Vs equal to R1 I1. Okay, so assuming VR1 is the voltage across R1, which is the same as Vs. Okay, so VR2 equal to Vs also, equal to R2 I2. VR3 equal to Vs, which is R3 I3, and VR4 equal to Vs, which is R4 I4. Okay, so then what do we have? So I'm gonna solve for I1. So I1 here will be Vs over R1. I2 will be Vs over R2. I3 is Vs over R3. And I4 is Vs over R4. So when I take this and I substitute that in there, so then the total current, which is in terms of the voltage and the resistance, which is Vs over R1 plus Vs over R2 plus Vs over R3 plus Vs over R4. So Vs is common, so I am going to pull that outside. So Vs, so 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, which is the total current supply. Okay, so now if I am able to replace all the if I'm able to replace this circuit with one equivalent circuit, okay, so if I'm able to convert this into Vs, right, and an equivalent resistance as we did for the series, right, the current supply is going to be the same because the network is the same. So Vs will be equal to R equivalent times I total. Okay, so that means I total will be equal to Vs over R equivalent. Right, so if I match that with what I have here, right, so then I have Vs over R equivalent, which is equal to Vs times 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. So that means 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. Right, so to find the equivalent resistance for parallel, for this 4 resistances connected in parallel, is 1 over R1 plus 1 over R4, 2 here, 3 here, plus 1 over 4. So that is when we have those 4 resistances connected in parallel. So in general, okay, so when we have n resistances connected in parallel, so some other scenario, so we have R1, so let's say this is Rn, we have R2, okay, and have this, we call it sharing the same nodes on top and bottom. Then R equivalent, okay, look into, let's say this is A and this is B, between the node A and B, then R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over Rn. Okay, so when we have n resistances connected in parallel, then this is how we calculate the total equivalent, the total resistance or the equivalent resistance. Okay, so that means if I had Vs and connected to A and B, where I will have all this resistance connected to, so Rn, so, and this is the total current. This is equivalent to the same voltage Vs. Right, so it's still A and B, but then we have the equivalent resistance connected to it. Okay, and the equivalent resistance is what we calculate over here, and the current remains the same. So I total and I total. Okay, so that's when we have resistances connected in parallel. Okay, so, and we also define the inverse of a resistance, which we call a conductance. So we know that a resistance is expressed in ohms, but G, which is 1 over the resistance, right, is called conductance. And that is expressed in Siemens. Okay, so that means we have 1 over R equivalent, which is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over Rn. So the equivalent conductance is just the sum of the conductances, right? G1, G2, and G3 and so on, where Gi is 1 over Ri. Okay, so now, so let's say we have an example. So let's say we have 2 resistances connected in parallel, for example. So if I had R1 here and R2 here, and I'm looking through here, A and B. Okay, looking there, and I wanted to find R equivalent. So R equivalent we know is 1 over R1 plus 1 over R2. So it's 1 over R1 plus R2 over R1 times R2, which is R1 R2 over R1 plus R2. So R equivalent is the product of the resistances, like when you have only 2, divided by the sum. Okay, so now let's do an example. Okay, so example. So example. Okay, so you're asked to find the equivalent resistance, the equivalent resistance connected between these 2 points A and B. So let's say we have the source, which is 120 volt. We have 4 ohms. So this is A, this is B, and let's say we have 18 ohms. Okay, and then we have 3 ohms, and then we have 6 ohms connected, 6 ohms. So let's say that we call this current I1, call this current I2. Okay, so find, so question 1, find the equivalent resistance connected to A and B, right? That from the left network. So A and B. So that means that's right, the equivalent resistance connected to A and B. So, and then find, so let's say this is IS, to find the current in each branch, the current in each branch. So that means find IS, I1, and I2. Okay, so let's solve this question. So solutions. So let's redraw the network over here. So I have the 4 ohms resistor, then I have A and B, and we have the 18 ohms, and then we have 3 ohms, we have 6 ohms. Okay, so now, so to find the equivalent resistance, all right, so we wanted to find the equivalent resistance looking through A and B. So looking, this is A and B, looking here. Okay, so that meant the network that's connected to A and B to the right is this. We have 18 ohms, and then we have 3 ohms, and we have 6 ohms. Okay, so if we look at this carefully, we know that the current I2 here is the same current as that's the current through the 3 ohms and the 6 ohm. So the 3 ohms and the 6 ohms carry the same current. Okay, so this implies that they are in series. Okay, so that means we can find that combination. So the combination 3 ohms and 6 ohms is 9 ohms. Is 3 ohms plus 6 ohms. They're in series, we can add them up. So that is 9 ohms. So that means my network now becomes, we have 18 ohms here, and this will be 9 ohms. Okay, so now that's A and B. So as you can see, 18 ohms and the 18 ohm and the 9 ohm are connected in parallel. Right, because they share the node A and B, right? Because they share nodes A and B. Okay, so to find that parallel, so I'll call it RAB. All right, so let's say RAB here. So RAB will be 18 times 9 divided by 18 plus 9. All right, so from the formula that we derive here, all right, from this formula, okay, so that's the formula that I apply. So that gives me 6 ohms. So that meant back to my network, what do we have? We have 120 volt. That's the 4 ohms connected to A and B. Okay. But here we have RAB, which is 6 ohms. Okay. So to find the current in this branch, what do we call it? We called it IS. So IS is the same through the 4 ohms and the 6 ohms. So that's implies that they are in series. Okay, so that means I can simplify this network down to 120 volt to 10 ohms. We're connected to that, and this is IS. So using Ohm's law, IS is the voltage 20 divided by 10 ohms, which is 12 amps. So we know the current into that branch, the source, the voltage source branch, which is 12 amps. Now, so that means we know the voltage across the 10 ohm. So since we know the current, all right, so let me redraw the network. So I'm gonna work my way up. So we have this. So let us find the branch current I1 and I2. So this is our network, 120 volt. Okay, have 4 ohms, have A and B here, and we know RAB. Okay, so we know RAB, which is 6 ohms, and then we know the current in this branch, which is IS. So that means we can find VAB, which is using Ohm's law. VAB will be RAB IS. So 6 times 12, that's VAB. Okay, so we know that voltage, so which is 72 volt. Now, so then I'm gonna draw the network still, and then 20 volt. So we still have our 4 ohms. This is A, this is B, and we know that the original, we have 18 ohms. We have 3 ohms here, and then we have 6 ohms there. So we know the voltage over here, VAB, which is the voltage here, VAB, across the 18 ohms. So we can find the current I2, I1, right? So that's the current to the 18 ohm, we call it I1. So I1, using Ohm's law, so VAB divided by 18 ohms. Okay, so 72 divided by 18, that's I1. And then what is I2? I2, we have the same voltage across that 9 ohms. So VAB divided by 6 plus 3 ohms. So 72 volt divided by 9 ohms. Okay, so when you put that in the calculator and then you calculate the voltages and you calculate the current I1 and I2, we must be able to check whether the KCL is satisfied or not, right? So that's how we can check the work, right? 72 divided by 18, that give me 4 amps, and 72 divided by 9 should be 8. Oh no, yeah, should be 8 amps. So when you write KCL at node, I have to check your work. Okay, write KCL at node A, right? So this is IS and this is I2. So IS equal to I1 plus I2. So what is I1? It's 4 amps. I2 is 8 amps. So the total is 12 amps, right? Which is check. Okay, so that's what we calculate IS to be, right there. So that proves that we calculate everything correctly. So example 2. So find the equivalent resistance connected to the voltage source. Okay, so we have 60 volt source, okay, and then here we have 18 ohms, we have 100 ohms here, and we have 25 ohms. Okay, and then here we have 40 ohms. Here we have 22 ohms. And then we have 10 ohms here. Okay, so to be able to do this, right, so what we're asked to do is to find an equivalent resistance that will be connected to the 60 volt source. Okay, so what we need to do, so we are going to work backward. We're going to work back and go to the voltage source. So you're gonna combine this and this first. We know that they're going to be in parallel, right? Because those two resistances, the 10 ohm and the 40 ohm, 10 ohms and 40 ohms are in parallel, right? Because they share. So let's call this node A, let's call this node B, and let's call this node C. Okay, so they're in parallel because they are connected to A and B, to node A and B. Okay, so that means that equivalent will be 10 times 40 over 50. Okay, the sum, right? 10 plus 40. So we have 400 divided by 50. So that's going to be 8. Okay, so then what is the network? I'm gonna redraw the network along the way so that we can follow closely. So our network now, so we have 60 volt, we have this 18 ohms, we have this 100 ohms, and we have this 25 ohms. Okay, and then we have this 8 ohms, and then we have the 22 ohms. Okay, so if we had the same current that will go to the 8 ohms, and so the current here is the same, so 8 ohms and 22 ohms are in series, so that means the equivalent will be 22 plus 8, so that's 30 ohms. Okay, so if I redraw my network, I will have 60 volt, still have the 18 ohms here, the 100 ohms here, the 25 ohms there, and then we have the 30 ohms. Okay, so now, so the 30 ohms, okay, so now what do we have? We have 30 ohms, 25 ohms, and 100 ohms in parallel. So the equivalent resistance will be 1 over 30. So 1 over, the equivalent resistance will be 1 over 1 over 30 plus 1 over 25 plus 1 over 100. So let's calculate that. That's 12. Okay. So then that gives me 60 volt. Then we have 18 ohms connected to 12 ohms. So the equivalent resistance in this case will be 12 and 18 in series. So the equivalent resistance is 12 plus 18 ohms. Right, so that's 30 ohms. So our equivalent is 30 ohms. Okay, so that is an example on how we can calculate this equivalent resistances. Thank you for watching, and please subscribe and like the videos, and hit the like button, please.